Good morning, everyone. Hope everybody is fine. Today is Thursday, the 12th of March, 2020. The subject or the things to be discussed today are the derivatives of the carboxylic acids, part 1. The first derivative to discuss today is the acyl chloride. The acyl chloride has the general formula of CnH2n-1OCl and a structural formula in terms of R of RCOCl. Now the R in this case could be replaced with the H atom, and COCl is C double bonded with an oxygen and single bonded to a chlorine. The name of the acyl chlorides is general name, that is, it's the alkanoyl chloride. For example, we've got one to name. From the left I will be reading the structure. It's CH3CH. CH is bonded to CH3, and then CH2, and then C double with an O and single with the Cl. The name of this acyl chloride is 3-methylbutanoyl chloride. Now, if you count, of course, the C double with the O is the one that is numbered 1. So the longest continuous chain starting from this carbon contains 4 carbons. Thus, we wrote down a butanoyl chloride. 3-methyl means that the methyl group is simply bonded to the 3rd carbon of the main chain of the butanoyl chloride. Another example here, we have the benzoyl chloride. As you can see, the C6H5, and then we've got the C double with the O and single with the Cl. This is one important acyl chloride that we deal with. Now, next on the slide, we need to be discussing the preparation of the acyl chlorides. Guys, we have 2 ways to prepare acyl chlorides. The first method is the use of PCl5. So when we put RCOOH, which is the carboxylic acid, plus PCl5, it produces the RCOCl, which is the acyl chloride, plus POCl3 plus HCl. Now the name of the PCl5 is phosphorus pentachloride. This is one method. The other method is the use of thionyl chloride. So we start with the carboxylic acid, RCOOH, plus the thionyl chloride, which is SOCl2, produces RCOCl plus SO2 plus HCl. Now, those are the 2 ways that we use to prepare acyl chlorides from the carboxylic acids. The hydrolysis of acyl chlorides. The acyl chlorides can be hydrolyzed, of course, by the use of water. So RC double with the OCl plus H2O produces the carboxylic acid RCOOH plus HCl. The characteristics of this reaction: it is very fast and complete, exothermic and vigorous. An important note here to pass along: any reaction that involves an acyl chloride must be carried out in a dry container to avoid the easy hydrolysis of the acyl chloride. So anytime you have a reaction that features an acyl chloride in its reactants, it must be carried out in a dry container or flask or whatever the dispenser you're using to carry out the reaction. It has to be extremely dry to avoid the easy hydrolysis of the acyl chloride. Okay, the second derivative of the carboxylic acid to discuss is the acid anhydrides. Acid anhydrides have the general formula of CnH2n-2O3. The structural formula is R single with a carbon. This carbon is double with an oxygen, then single bonded with an oxygen, then this oxygen is single bonded to a carbon, and this carbon is double bonded with an oxygen, and then single bonded with an alkyl group R or R prime. Now the alkyl groups R and R prime could be replaced with H atoms. The functional group of the acid anhydride is a huge group. Anytime you see C double with an oxygen, then single with an oxygen, then the oxygen is single with another carbon and this carbon is double with an oxygen, you are talking about the acid anhydride functional group. To simply abbreviate that huge monster of a functional group, we always write down COO, then CO. This is the functional group of the acid anhydride. Let me repeat, anytime you see carbon, two oxygens, then carbon and oxygen, this represents the functional group of the acid anhydride. Now the naming of the acid anhydrides, we have two methods to name I should say two cases when it comes to naming the acid anhydrides. The first case is when the R and the R prime are identical. In this case, the name of the acid anhydride is alkanoic anhydride. For example, if you have CH3 single with a C doubled with an oxygen, then O in the middle, then C doubled with an O and single with the CH3. As you can see, if you look at the oxygen in the middle, the oxygen is somehow acting as a mirror. So you're just showing the identical structures on both sides of this oxygen. Since R and R prime are identical, we call this ethanoic anhydride. I want to repeat. Looking at the structure, we have an oxygen right in the middle, and it's acting, so to speak, as a mirror. When you look into the mirror, you see your image. So the oxygen right there is acting as if it were a mirror. Looking at both sides of this oxygen, you notice that we have COOCH3, COOCH3. So both of these two structures, which are alkyl groups, are identical. Therefore, the name is ethanoic anhydride. Now, the second case is when the R and the R prime are different. Then we have to use compound names and alphabetic priority should be applied. What is meant by that? If you look at the structure at the very bottom part of the slide, we have CH3 single with a carbon, then this carbon double with the oxygen, then single with an O, then C double with an O, and then CH2, CH3. If you look at the oxygen, which happens to be the one in the middle, you can see on its right side, we have C doubled with an O, and then CH2, CH3. And it's on left side, we've got C doubled with an O and CH3. The one thing to notice right here is the R and the R prime, which are the two alkyl groups that are connected or bonded to this oxygen, they are different. In this case, this is called ethanoic propanoic anhydride. As you can see, the name is a compound name. It contains two names, and we're using alphabetic priority. Now, the E, of course, comes before the P. That's why we call it ethanoic propanoic anhydride. Now, where is the ethanoic part? The ethanoic part is on the left side, where you can see the CH3 single with the C double with an O. That is the ethanoic part. The propanoic part is on the right side, where you see C double with an oxygen, then CH2, then CH3. This is three carbons, so it is propanoic. So the name is ethanoic propanoic anhydride. Always, when the R and the R prime are different, we have got to use compound names with the respect given to the alphabetic priority. Now guys, we need to explain the preparation of the acid anhydride. As we said, acid anhydrides and acyl chlorides are derivatives of the carboxylic acid. So they need to be derived from the carboxylic acid. Now, in order to prepare an acid anhydride, we need one process to be carried out. It's called the intermolecular dehydration of two molecules of carboxylic acids with the use of P2O5, which is called diphosphorus pentaoxide, which is a very strong dehydrating agent which assists in absorbing the water molecule from the two carboxylic acids. Now, what is meant by intermolecular? Intermolecular means that it is a reaction between two molecules. Intra is within the molecule, inter is in between two molecules. Dehydration is the removal of a water molecule from the two molecules in this process. Now, generally speaking, we need two RCOOH, which is two carboxylic acid molecules, And this reaction is an equilibrium reaction with the use of the P2O5. The P2O5 assists in simply absorbing or just taking the water out of the two carboxylic acid molecules, leading to the formation of RCOOCOOR plus H2O. Now, according to Le Chatelier principle, what happens when we simply remove water? As you continue to remove water from this process, what happens here, according to Le Chatelier principle, this equilibrium will shift forward, meaning that we increase the production of the acid anhydride. That's why the P2O5 plays a major role as a catalyst in this reaction, because it assists in absorbing the water and eliminating more and more of the water molecules from the carboxylic acids, therefore pushing the equilibrium or the reversible system forward, thus increasing the yield of the acid anhydride. I give an example right here. You got 2CH3, CH2COH with, of course, the P2O5 produces CH3CH2, C double with an O, single with an O, another C double with an oxygen, then CH2CH3 plus H2O. Now, of course, the name of this, since it is coming from propanoic acid, the name of the anhydride in this case is propanoic anhydride. Remember, when the R and the R prime are both identical, it is only a single name for the anhydride. So you start with propanoic acid, you end up with propanoic anhydride. You start with butanoic acid, you end up with butanoic anhydride. Of course, the starting of this reaction has got to feature two molecules of the carboxylic acids in order to form the anhydride. Another way to look at it, propanoic acid contains 3 carbons. When you look at the anhydride, it contains 6 carbons. If you start with the butanoic acid, it contains 4 carbons. If you look at the acid anhydride, it contains 8 carbons, simply because we need 2 molecules of the carboxylic acids in order to form the acid anhydride. Now, last but not least, it's the hydrolysis of the acid anhydrides, just like its other derivative, you know, the one that with its predecessor that we're talking about, the acyl chloride. We said acyl chloride, when used in a chemical reaction, has got to be the chemical reaction that is conducted in dry containers. The same thing or the same precaution must be dealt with when we have acid anhydrides. We have got to have acid anhydrides reactions done in dry containers to avoid the easy hydrolysis of the acid anhydride. As mentioned on the slide, we've got the acid anhydride, which is RCOOCOOR, plus the H2O producing 2 molecules of the carboxylic acids. It is just the total opposite of the preparation of the acid anhydride, but in this case, this reaction is extremely fast, it is complete, it is exothermic, and of course it's vigorous, just like the characteristics of the absolute hydrolysis of the acyl chlorides. So let me recap. Anytime you have acyl chlorides or acid anhydrides, ladies and gentlemen, they have got to be conducted in dry containers to avoid the easy hydrolysis of either the acyl chloride or the acid anhydride.